Thank you so much. Thank you so much. Thank you for joining us for this talk. This is the second time we're giving this talk, and last time it was in the very same room and almost the same time. So there's very high chance that it's going to be here again if we ever do it in future. But thanks for coming. My name is Jakub. I work for a company called Freeport Metrics. I will be presenting with Marta from Ververica, and basically we at Freeport Metrics we use the great product Apache Flink that Marta is working on with her colleagues at Ververica. And what we'll talk today about, first of all, I will talk a little bit about what's so specific about IoT applications and IoT data. Then Marta we will walk us through about how Flink is useful for this type of applications. Then I will talk about the specific use case that we created at Freeport Metrics using Apache Flink, and then Marta will follow up with additional use cases of people using Flink for similar projects. Okay, so just a brief recap. What's so special about IoT and data and applications? So when creating this application, first I thought how much IoT data there is, and more specific, how much IoT data I produce. And I'd like you to walk together with me through this very quick exercise. When thinking about how much IoT data I generated last month, so maybe you drove through an automated toll booth at the gateway, or maybe you used an electric scooter, or maybe you went from a run and your pulse and your run was recorded and stored in the cloud. And then think about how much data I generated last week. So I did a checkout at a automated I did an automated checkout at the retail store. I used GPS, and probably my data is stored somewhere for statistics or other purpose, and maybe on a smart fridge or other smart device. But I think what is the most interesting is when you think how much data you produce constantly. And maybe your house is connected to a smart meter that tracks your energy usage, and every time you turn on your coffee machine, this spike of energy usage is recorded. Or maybe you're constantly tracking your life with a health tracker, or maybe unconsciously when your phone is connecting to a cellular base tower, this data is stored somewhere and used hopefully for good purposes. So to summarize, there's a lot of data in everyday life, but also I'd like to talk today about some industrial use cases. Some can be measuring solar energy production at solar farms. Maybe some of you arrived using a plane here, so maybe your luggage was tracked automatically at an airport. There may be also a use case of sensors tracking things very quickly when they go through production line. And there are more and more use cases. Some of the most interesting ones are predictive maintenance, when you track data from vehicles or other machines and you try to stop them and the maintenance before they break. The whole trend on smart buildings and smart cities also is very interesting from the data perspective, as well as all the use cases in healthcare. So, like we established, there's a lot of data. Cisco says that it's like 500 zettabytes produced this year. The number seems a bit abstract, but I think what is important is there's more data produced that can be stored in all the data centers. So it means that if we want to use this data effectively, we need to process it before it is stored. Or we don't store it at all, just process it. Another IoT property that is very often connects through a unstable connection, like mobile connection, you very often use gateway devices, which are devices living on site and serving as an intermediary between IoT devices and your data center. And those gateway devices can use buffering, cause additional delays, and of course you need to take failures into account as well. And the last property is that data flow is usually continuous, especially in the when you track statistics, or let's say you collect data from sensor every minute. The flow is continuous and built up. Data volume builds up through time. And going to IoT applications, I think what's unique about them is that first of all, they collect data from real world, and they need to trigger reactions in the real world, which needs to happen fast. To give you an example from a system that we built, which is an asset tracking system, you can track all the hardware in your company, and let's say you have a precious laptop that is about to leave your facility, so you want to know sooner than later that you can react. And I will stop here and let Marta talk about why Flink is good for these scenarios that I talk about.
Thank you. Okay, so Jakub just gave us a quick rundown of the basics of IoT data and IoT applications. I will be trying to tell you about Apache Flink and what characteristics it has that makes it a good fit for the requirements that this kind of applications have. So I see some familiar faces from the Flink community. But for those of you who are not familiar with what Flink is, just going to give a very quick overview. Flink is a distributed system for stateful stream processing. It allows you to perform stateful computations over unbounded data streams. This, in practice, means that it's capable of processing data that is continuously arriving in real time, and also that it can remember data in flight that it can use in between computations. Flink is also optimized for to do these computations in memory speed, so very fast, and pretty much at any scale that you require from it. And one of its most notable properties is that it very easily maintains very large state, application state, and in a disaster-proof manner, which means that it guarantees that your application state is never lost, even in, and can always be easily recovered, even in very bad disaster scenarios where everything fails. And because it's distributed systems, likely everything will fail at some point. So now that we're hopefully all on the same page about what Flink is, I'm going to give you or guide you through 7 reasons why it's valuable in the IoT scenarios that Jakub was talking about. So for the first scenario, Flink has a lot of native properties that allow it to handle and process events with very, very low latency. And this becomes very important if you consider that, like Jakub told us before, IoT applications are operating continuously, and they are already affected by latency that comes from network transmission or just failures that happen at the edge. And so, we should try to minimize also the latency that is added on the data processing side. And so Flink is able to achieve these low latencies by having state always locally maintained and accessed either on heap or spilled to disk if your state becomes too big. So your application state is not maintained in some distributed database over the network that will add even more latency because you're trying to communicate with it. So the state is just really co-located with the computations and in the machine that is processing the events. So this gives you very, very fast state access whenever you need to access it. And this low latency is achieved also through Flink's, the way Flink's network stack is built. It's optimized to achieve low latency, but also offer you at the same time very high throughputs. This is done with a little help of something that is called credit-based flow control, which I'm not going into in detail, but I just linked here. There's a very good series of blog posts on the Flink blog about Flink's network stack and how this is actually materialized. And another point is that the way that Flink keeps this state consistent is by using something that is called a checkpointing mechanism. In the end, this is just guaranteeing that you take periodic snapshots of your application state that, that it could then use to just recover upon failure. But these snapshots can be taken asynchronously and optionally also incrementally. So it means that you can have a robust, consistent application without actually adding any overhead latency that results just from that process. Okay, as I said before, Flink is a distributed system, and it can scale to very huge data volumes. The way it scales is basically that streams are partitioned to distribute data and computation on your computing cluster. So out of the box, all your applications are inherently parallel and highly scalable. There are a lot of, so that you have an idea of the scale that you can achieve with Flink, there are production use cases that run Flink on more than 10,000 cores. And as a actual particular example, Netflix is processing around 3 billion events per day with Flink, powering a lot of their business critical real-time applications. Along with the streams, also the application state is partitioned with it. So as I said before, everything is co-located. And the way that state is managed, you can consistently scale it to dozens of terabytes of state. And yeah, another advantage is that whenever you want to update state, because everything is co-located, you don't have a lot of transaction overhead just because updates are, in the end, just local operations. And yeah, even though most IoT applications operate in a continuous fashion, there's also the cases where you have load spikes. And Flink helps you with that because it can be scaled in and out on demand. So you can easily adjust things like parallelism to ensure that the performance is accompanying the load that you have in your system. So for number 3, I think it's widely known that IoT data or sensor data in general doesn't have the best quality. So it can be super noisy, and a lot of times it's out of order or late when it arrives to your system. And I would say that Flink handles this very gracefully because it has very rich time semantics. So Flink allows you to process events based on the timestamp of when they actually occurred in the real world, which is called event time, as opposed to when they arrive in your machine for processing, which is known as processing time. And this means that regardless of the order in which the events arrive, Flink can guarantee that you process them in the order that they actually occurred in the real world in the first place. And in addition to the event time, Flink also implements this abstraction called watermarks. Yeah, I think you can easily go on for hours about watermarks, but the gist of it is that it's something that allows you to track the progress of time in your system, and it also allows you to say when you're done with processing. So you're done waiting for data that is late, and then you can just choose to do whatever is fit for your SLAs or for your completeness requirements. So you can just wait for late data redirected to some other system to be processed in a different way. Or you can just, if you have that privilege, you can just discard those late events. And here you always have, depending on your requirements, there's always a trade-off between how complete your result will be and how much latency you're adding to the system by allowing this lateness to some extent. Also, still regarding noisy data, Flink has built-in primitives that help you smooth this data. So things like windowing, you can very quickly define some windowing function that lets you average over your data, or just implement some other kind of more sophisticated pre-processing to your data. Like I mentioned, for instance, at Netflix, they use Flink to power a lot of applications that are business critical. And so when you have business critical applications, you also need to ensure that you can guarantee very high uptimes. And Flink has a very robust fault tolerance mechanism that backs this up quite nicely in production scenarios. And yeah, basically, like I mentioned before, it has a checkpointing mechanism that takes consistent snapshots of your application state, stores it in some persistent storage like S3 or HDFS. And when something fails, your system breaks down, you just restore the state, and your application is recovered like nothing happened before with exactly once state guarantees. And for some combinations of syncs, so if, for instance, you're using Flink with Kafka, you can even achieve end-to-end exactly once guarantees, which is pretty much all you want, I guess. In addition to this, you can also set up Flink for high availability scenarios with many different resource managers. So even if you have, even if your master node goes down, you can guarantee that your application is easy to recover, and you can just like keep processing with very little downtime. Also, like Jakub mentioned, something that is very common in IoT is that you want to act upon a certain predefined series of events and then trigger some downstream actions. So you might want to generate an alert, or you want to trigger a cascade of business processes. And so Flink allows you to very easily define a regular expression like patterns and then match them to the event streams that are incoming. So if you say, hey, I wanna send out an alarm if I see event A followed by event B or event C, and then followed by event D, you can just define that pattern you deploy your application, and basically all the streams will be continuously monitored for looking for this pattern that you defined. And the good thing is that pattern matching you kind of have a lot of choice in Flink. You can do it more programmatically, just like with Java or Scala code, just using, there's a dedicated Flink library. It's called Flink CEP. CEP standing for Complex Event Processing. Or you can do it in a more high-level code-free style, just using streaming SQL, because the Flink SQL semantics were extended with the match recognize clause. I also linked a blog post here that I actually wrote if you wanna learn more about pattern matching using SQL for streaming. And yeah, because Flink has more functionalities than just doing pattern matching, you can very easily combine it with more advanced data analytics. So you can basically cover a lot of more complex scenarios where you need to do some complex event processing. Yeah, if you want to check, I know another reference, but the AWS guys last year released a pretty cool demo that is using the Flink CEP library for real-time bushfire alerting. And yeah, you can also check it out. It has really nice heat maps and a lot of visualizations. It's a really cool demo. Okay, number 6 is a very quick one. Flink is well connected with external systems. So it is supported by a large ecosystem of connectors that are maintained by the Flink community. And this means that you can basically integrate Flink with most modern IoT architectures. So you can, out of the box, just integrate Flink with popular messaging systems like Kafka or Kinesis or Pulsar. Same thing for databases and key value stores. File systems, like I mentioned, for instance, for checkpointing, and then, or you can just, dump your data into Parquet, something, whatever fits your needs. Okay, and lastly, a bit of a bold statement. That's why I'm attributing it to Fabian. We can argue that data streaming is conceptually simple. At least for IoT data, it's a very natural way of processing data, because what you have is continuous streams of events that you want to process immediately, and you want to process them event by event. And this is something that is native to the way that Flink does stream processing. So it's actually a no-brainer. Yeah, and Flink also gives you very good tools to reason about time and ordering, like I already mentioned. And yeah, Flink in general can just make stream processing less complex, or at least less complex than it needs to be, and offers you natively a lot of handy built-in operators, so like windowing operators or joins or complex event processing. But it also still gives you access to the very core primitives of Flink, like state and time, that, as we've seen, is really, really important to tame your application. And you can just use it at whatever scale you want, because it will parallelize and scale applications independent of the size of your incoming data. It will maintain whatever size of consistent state and guarantee that your application can always be recovered. Okay, so with this very long introduction, I will hand it over to Jakub again. He will tell us about how they built an asset tracking system with Flink at Freeport Metrics.
Thank you. So I will talk about our experience with Flink and how we use it to build products for one of our clients, Evan Howe. We didn't use all the great features that Marta presented, but I will talk about those that I think were the most useful in our case. Just a very quick about my company I'm working for. We are a B2B digital product development company, and what it means, we create software for companies that sell software to other companies. That's simple. We worked with quite a few data analytics projects so far. With solar and wind data, we did quite a few projects in warehouse and inventory space. We work with automated retail kiosks and also with sustainability reporting. And I think what is important to mention that this was our first project with Flink, and before that we relied on standard ETL tools or custom solutions when we need to process data in real time. Okay, so what an asset tracking system is? First of all, what do you use it for? The most basic use case is inventory management. So basically, you want to know what things you have, do you have all the things you need, and if they are in place, they should be. Another use case is tracking shipments in warehouses, and I think, asset tracking is not about things. One of the cool examples, and actually our first pilot, was tracking patients in hospitals. So patients when handed RFID wristbands, and their progress through medical procedure was tracked, and it was displayed on a dashboard in the waiting room, so patient families could stay informed about where their relatives are right now and what's happening to them. And data sources in the inventory tracking system that we created are RFID tags, which are tracked by RFID antennas in real time. Operators can also use handheld scanners to scan RFID tags as well as barcodes, and of course there is a user interface where you can override different values and enter data manually. The system needs to scale from small use cases to thousands of hundreds of assets. And on the tech side, it was a classic IoT thing with gateway, and we had Kafka in the middle, and Kafka forwarded data to Flink. So speaking about features that we found very useful, I think the most important is event time. In our case, we had multiple data sources, we had gateway devices, so all those events come to our system at different time, but we need to process them in order they occurred. So Flink event time processing was very useful in our case. And another feature, windowing. Antennas can scan RFID tags constantly, and you can imagine a situation when there are two antennas next to each other and they overlap. So we used windowing to apply some logic that let us know to determine which antenna we should assign given tag to. So again, thanks to Flink windowing tool. The second thing is Flink's state. First of all is the concept of partitioning by keys, which is a kind of natural way to do in Flink. And what it gives to you is that basically your workload can be easily parallelizable. In our case, we grouped events by tag. And when you combine event time and when you combine how Flink handles state, you can build simple state machines. We haven't used complex event processing that Flink provides. We built our simple business processor, and which let us do things like tracking if a patient is enter a waiting room, and when the patient enter doctor's office, and then recovery area, and that we could set a timer for 10 minutes, and then we could automatically transition the patient to another state. So again, very useful combination of using state and event time. Very briefly, our dev experience with Flink. First of all, we could have quite a few components to build in this system. Event processing was just one of them, and we, thanks to efficiency of Flink, we were able to achieve our goal, which was building the system. Second of all, we could focus on logic, referring to what Marta said about Flink being conceptually simple. I have to say that when you master this concept, or at least get familiar with it, it's a relatively natural way to think about processing continuous stream of events. The first thing is high-level abstraction, which is very good for entry barrier, and also low-level abstraction, so you can expand given areas of your application as you progress in development and in your Flink knowledge. Needless to say, integrations with Kafka is really good in Flink as of now. So talking about challenges, and again referring to Flink being conceptually simple, for us coming from more traditional background, and I dare to say that it may apply to many people entering stream processing. This was like a totally new way of thinking. It's just not just another framework that you add to your Java Spring application and you can immediately write things. So you need to understand concepts to use it. Second thing is that in this model of processing, you have data together with processing code, and you need to really think really carefully how you design your programs and how this affects the rest of the system. To give you an example is, for example, how you partition your state. What do you choose for your keys? Maybe a little bit hard to change later, or at least some significant changes needs to be made if the rest of the logic already relies on this partitioning. So we need to plan ahead. And last thing is not valid anymore, but 3 years ago, learning materials were limited. Now there is a great Flink book, which I highly recommend. It came out this year. There are trainings, there are a lot of online videos for different conferences, so I think it's really good position right now for people who want to enter the Flink world. And that's all from me, and I pass it over to Marta again to talk about whatever smart people did about IoT.
Okay, so now we heard about how Jakub in Freeport Metrics uses Flink. I'm not going to burden you with very detailed IoT use cases, but I would like to mention a couple of other use cases that we have with users in production. All of these I will present or briefly explain 3. All of these are based on existing talks from Flink Forward. So again, link dropping. Every slide has a link to the talk that the use case actually refers to. So if you want to really dig into the nitty-gritty of how they used Flink for their particular use case, you can just watch the recordings. First up is John Deere. John Deere is a Fortune 500, pretty old company that manufactures high machinery or heavy machinery for agriculture, construction, and forestry. And it uses Flink to power a data platform that helps their customers improve the efficiency of their farming operations. So just so that you have a rough idea of the scale at which they operate and use Flink, their data platform receives around 4 billion events per day, and a single machine can be producing around 2.5K measurements per second. And they also, in the talk, they explain how they faced some of the challenges that we described here. So, for example, having machines operating in rural areas that have pretty poor network coverage. And yeah, also like the spiky data that results from that. And they also talk about how they use Flink to do some pre-processing and some cleaning of their data to then just store it in a data lake for further processing or for further analysis and visualization. And their stack is basically AWS based. They deploy Flink on EMR. They use Kinesis for data ingestion, Flink to process, and then they just dump everything into a data lake that is based on S3 and DynamoDB. Another use case is from a company called Here. It provides mapping and geolocation data and other related services. They use Flink to power something that sounds very esoterical. It's called living maps. But in the end, what it does, it collects IoT events from multiple car sensors. And then they use a Flink application to enrich static map data with this live location context data to account for things like road conditions, accidents, availability of parking spots in real time for the customers that subscribe to these living maps in their data marketplace. And lastly, we have also Track Unit. It's a bit similar to John Deere. Track Unit basically provides telematics solution for fleet management in the construction industry. And they basically use Flink to build a pipeline to process any telematic IoT data that they receive from the machines. So they track things like where where machines are, what they are being used for, when they are having idle time, so when they are not being used. And they use the insights that they derive from this to optimize the usage patterns of the machines and also to infer about maintenance needs and other similar scenarios. So they're also deploying Flink on EMR, using Kinesis, Flink for processing, and then as a sync, they're using Cassandra. Okay, so to wrap it up, we tried to explain you how Flink meets the high demands of IoT applications. In a very brief summary, it gives you a very reliable performance and failure handling. And it, at the same time, gives you enough flexibility to build very complex application logic with the right tools that allow you to overcome a lot of the bottlenecks that are inherent to working with IoT data in IoT pipelines. So, yeah, Flink is being used a lot in production for these use cases. If you have a nice project coming up with IoT, you should maybe give it a try. Let us know how it went. And thank you.
So if anyone has questions, we can start the Q&A.
I come from a very scientific background. I am curious to know some numbers behind your latencies. So for example, the facilities that I work with, fusion machines, they have 1 kilohertz, 10 kilohertz control loops. The stream processing seems ideal. They've got to look for a host of different situations that happen. They've got to respond to them. You're doing magnetic confinement, but the latencies are quite low and you need reliable 10 kilohertz control loop. Is this possible? Is this achievable with Flink?
I can only say that in our case, the latency was a couple seconds. So, but I'm referring to Marta to answer what are the possibilities. In our case, it was enough, right?
Yeah, I don't think I can tell you exact numbers, but I think it's one of the things that Flink is really valued for is that it really achieves very, very low latency. So you have a lot of use cases with Flink for example, fraud detection, which has very, very low latency as SLAs. And yeah, Flink is able to cover that. I mean, maybe Stefan can give you more precise numbers. I think my brain is dumped by now, so.
Okay, I think this depends a bit what your SLA on that latency is, I guess, right? So there's, let's say when the system is, let's say, running in a happy state, not a machine just crashed and it's recovering from that, then depending on how you flip some switches, yes, you can actually get, even with multiple aggregations and so on, like easily single-digit milliseconds or single-digit milliseconds. Yeah, that works. No, it's not built in like for that area. So it's not something that you would use, I don't know, on a high frequency trading platform. No, it's really the, let's say, the low milliseconds range. If you consider a situation where, you know, a machine just crashed and it recovers, then, and this is a bit of a tricky question. I mean, usually, you know, before you actually detect a failure, you're waiting for a few heartbeats to time out. That usually means 10 seconds already passed before you detected the failure. Then you have a little bit of like rebalancing work and so on that is ongoing. So that after the nines where you guarantee the low latency, it definitely goes more to the seconds, unless you go for like some active setup or so where you basically mirror the computation. Then you can actually like reliably keep it low. But yeah, it really depends very much on how you set it up. But I think microseconds is, I don't know, maybe nobody's really tried it out. I would be really curious what the answer, but that's not anything we've tried so far.
Thanks, Stefan, and thank you.
One hand. Okay.
Actually, I have a question about Apache Beam. So Apache Beam uses Flink as one of the runners. I would call it a different layer of abstraction. And my question would be, if somebody was to decide if use the Apache Beam or use a plain Flink, what are the advantages of one or other approach?
Again, I can give you, I think, a very basic answer, but good thing about ASF conference is that we have a PMC for Beam here. So, or at least a PMC for Beam. So I think the advantage that I see out of the box with Beam is just that if you need multi-language support, so if you need to use Python, it's probably gives you an edge because Flink is currently just the Python support is being reworked right now. But other than that, I don't really know enough about Beam to answer that, but I can gladly pass it to Max.
All right, I also have another question. Well, to answer your question, I think, Marta, you already explained it fairly well. So there are three main reasons why you would use Beam. So one is the unified API. So you have an API that supports both batch and streaming, whereas Flink has two APIs, although eventually I guess Flink will also have a unified API. So that argument might go away in the future. Then you can choose your execution engine. Like you can run on Flink, but you can also run on other systems like Google Cloud Dataflow, Spark, and others. And you mentioned already the multi-language support, the Python support, which can be really handy depending on whether your organization wants to use Python. Yeah. And can I ask another question? Sorry, yeah. I was just curious about, or maybe you touched upon this and I didn't listen carefully, but when you have data from like these machines, like let's say in a factory, and like how do you typically read, like do you have a recommendation how to read that data? Because there might be some obscure interfaces. I know there are some projects in Apache also which address this problem. as far as I know, Flink doesn't have like MQTT support, or I don't know how these crazy protocols are called. Yeah, how do you get the data into Flink?
Okay, so from my experience, you know, I think it's quite natural to use Flink behind some kind of event, something like Kafka. So how to get, or another similar system, so how to put events into Kafka on similar system is outside of the concern of Flink, I would say, but there are a couple different connections, but I don't know if there's anything for MQTT.
Yeah, I don't think it's actually something I never thought about before. So thanks. Yeah, I think that at least all the IoT use cases that I'm familiar with use always a queuing system in between actually the edge and Flink. So I don't know how to answer if you can just directly ingest things to Flink. Not with the connectors, I know, but I'm also not an expert in IoT. So yeah, I don't have a good answer for that.
So I have one for you. So same as the Beam one, like it sounds like a processing system. So like how does it differ from Apache Spark, where you can again just stream stuff and process it? And so I think maybe the stateful thing is something different, but like, can you more touch upon it?
Yeah, I think there's always someone asking about the difference between Flink and Kafka Streams and Spark. And I mean, the answer is that it really depends on your requirements, and also depends on what you're already using. So if you're already using Kafka Streams is just an API on top of Kafka. But if you maybe want to use a different queuing system, then Flink is basically compatible with all of them. And yeah, then it just really boils down to your requirements. If you're heavier, like on the batch side, on the streaming side, if you need low latency, also how important state is for you, because yeah, Flink has a lot of things that are very mature, so like state management and that kind of thing. So yeah, the politically correct answer is it depends very heavily on your use case and what you're already working with and what your team is familiar with. So yeah.
And do we need any other setup, any database for the state thing? Where do you store the state?
No, the state is stored either on heap, so like in memory, or it's stored on disk on embedded RocksDB key value store. So the idea is that you can keep very high volumes of state without needing to have an external system to keep it.
Yeah, I have a question about, excuse me, an apparent contradiction, right? Which is like you said, oh, you can have, 40 terabytes of state. I forget the number, but a lot of state. And you can also always have the state available locally to do your processing very quickly, but and it's sharded. So, but I think obviously you're not having all those 40 terabytes on every node, so they can't all be local. So you have to have decided to shard it in an intelligent way so that the data that you need is near the events that use it. But sometimes you have to do like join operations, grouping, across multiple partitions. And I wonder, like, does Flink handle that case? And yeah, if you can just address that a little bit.
Yeah, I think that the way that it's handled is it just reshards state when those operations happen. But Stefan?
Yeah, okay. So there is support for grouping operations. I guess that's really the question.
Yeah. So you shouldn't have any problem with that. So state management in general in Flink, I would say, is very advanced. So yeah,
Okay. And what if you want to control the sharding? Is that something that's under the user's control? Like if they know?
I see yeses, but I wouldn't know how to justify that. So if Stefan maybe wants to say something.
Yeah, maybe one confusion is that there's not one state. It's not like there's one database, but you have multiple stages in the processing pipeline. Let's say the first stage does joining by I don't know, by user ID. The next one does an aggregation by some other key, right? And between these, like each stage has its own state, sharded in a different way. And between stages, the streams are basically rerouted so that always events and state basically become co-located. So whenever the operation happens, they happen together. But the events can stream multiple times back and forth between multiple shards to meet the state in different stages as they need to meet it. And basically the sharding is, yes, you're defining by what key do you want to group or aggregate or anything that defines both the sharding and the routing and everything kind of together. And yeah, it basically like reshuffles the streams in memory to meet the shards at each stage as needed.
Any more questions?
Sorry, mine's a bit of a basic question, but you mentioned that it handles unbounded data. Could you just clarify what that means and how it does it?
Basically, Flink is or was purposely built to just handle streams that don't have really an end. And yeah, so the special thing about it is that it handles that continuous data event by event, which is a bit different than how other systems do it. But Flink considers batch or bounded streams just like a different way of looking at an unbounded stream. So Flink is also, by just considering that it processes unbounded streams, it just basically says that with the same system you can process infinite or finite data sets. So for Flink, you really, I mean, for now, like Max said, there's still some distinction. It's not fully unified yet, but in the future you will have the ability to just process both streaming and batch under the same runtime with same APIs.
Right, so the unbounded processing really is the batch processing, is that?
No, unbounded is the streaming.
Ah, okay, right.
And bounded is just, means it has a beginning and an end, which can just be a subset of an unbounded stream.
Right. So in terms of Kafka streams, I don't think Kafka streams has the unbounded concept, if my memory serves me correctly.
Yeah, so Kafka Streams also does stream processing. I'm not sure if they have support for batch.
Oh, see, sorry, I meant, yeah, there's no batch concept in Kafka streams. So yeah, so
that's so Kafka
Streams,
Streams, same thing, is just unbounded
okay.
continuous data. Yeah.
Oh, interesting. Okay, thank you.
Okay, so we'll wrap up here. If you have any more questions, I think Marta and Jakub would be happy to help you offline. Thank you, everyone.
Thank you.
Thank you.